Lesson on continuity. I cannot stress how extremely important continuity is. You'll have to stop and decide so often if something is continuous, because a lot of what we learn does not even apply if the function's not even continuous. So this is like something you will state quite often, and it's has to be and best to state it in a certain way. All right, so I'm just going to kind of read this to you, sorry. If we referred to a well-behaved function, well-behaved functions allow us to find the limit by direct substitution. So that means nothing's tricky about it. We just fill in the number first, and that's our answer because it exists from the left and the right. Well-behaved functions turn out to be continuous, like they actually land on that number and they approach it from the left and the right. And this section will discuss continuity at a point. So we want to look at if it's continuous at a point, and then sometimes we can say it's continuous everywhere, continuous on an interval, and different types of continuities. In non-technical terms, a function is continuous if you can draw the function without ever lifting your pencil. But you wouldn't want to say that on a calculus test. But it's continuous if I can just like keep on drawing it and never lift up my pen. The following graphs demonstrate three types of discontinuous. Like here I am trying to draw it. The limit exists, but there is no point right here. So I'd have to pick up my pen and step over it, even though it's infinitely small. This one's obviously not continuous. It has a vertical asymptote, and this one has a jump. You're not really going to be asked to like write the words for these, but you need to know them. Removable discontinuity means that I could actually put this dot in this hole and make it continuous. Okay, so that's it's called removable because I could easily remove the fact that it's discontinuous. There's non-removable discontinuity that is often referred to as a jump, or infinite discontinuity, which a vertical asymptote would give you infinite discontinuity. There's also another kind that is really weird that I've shown you time at least once on video. It's oscillating. Like a real typical example of this is this function does not exist at 0. There's not really a hole there. What happens is if you study it, it comes in and jumps around from both directions, but it's still just going up and down as it gets closer to 0, and it's oscillating. You can't grab it and change it. But this one's infinite, and this one's jump, and this one's removable for what all that counts for. You're not going to have to really call those. One thing you are able to say, and I'll reiterate this, all polynomials are continuous, as well as sine and cosine. And you're allowed just to say that it's continuous. You don't even have to prove continuity for those unless you're asked to. All right, so what constitutes this? Let's see. To say a function is discontinuous is not sufficient. We've got to be more exact than that in calculus. We would like to know what type of discontinuity exists, and if the function is not continuous, how could we make it continuous? And we could make it continuous on a removable discontinuity. Otherwise, we say it's a non-removable discontinuity, and it's a pretty like severe discontinuity where you had to jump or go off to infinity. Once again, we say removable discontinuity if there's a hole in the graph. Again, all polynomials are continuous. Okay, so let's move this up. All right, which of any of the three graphs have removable discontinuity? So let's look at example 1. All right, example 1 does not have removable discontinuity. There is removable discontinuity if I could fill in that point right here, but it is discontinuous here and it's discontinuous here, but it is not removable. This part right here is removable. This jump is not easily fixed. Find the points on the interval. Okay, so I guess let's move on. I don't really even know this worksheet I just pulled up because it looked good, but I'm not sure what it means by of the three graphs. Oh, of the three graphs above. I'm sorry, I didn't read it well. Of the three graphs above, it was the one that I showed you with the hole in it. All right, so down here, find the points at which the function above is continuous. All right, so this function is continuous a lot. There's lots of places where I can draw without picking up my pen, so it is continuous on these intervals. From 0 to 1, not inclusive, and is continuous again from 1 to 2, not inclusive. This is continuous all the way from 2 to 4. All right, so those are where it's continuous. It has places of continuity. There are intervals where it's continuous, but on the whole, this is a discontinuous function on the whole for two reasons. All right, now let's look back at this. See this sharp corner? That's going to be important when we get to derivatives. I could say the slope before it and the slope after it, but I can't really name the slope at that point, which is going to be a big deal later. Okay, so if you're looking at an interior point, a function is continuous at an interior point if this happens. And I'm going to talk you through all of that. In fact, this is called continuity at a point. You're just not looking at the endpoints. You're looking within the graph. Is it continuous? All right, so this states like all three conditions that have to happen. So let's see. The limit exists if the limit from the left and the right are equal, and it applies that there's also a function at that a value for the function at that same point or at that same x value. And we'll worry about endpoint in a minute. What we've got to do here is we've got to show three things that is described right here. All right, so I'm going to draw a picture of it after a minute. So first, you have to at least verify if there is a f of c. So I'll say f of c or f of x exists. C means like an extra special place. So first of all, we would say that, let's say f of c is defined. An example of that would be something like this. If I'm asking you if this is continuous at 3, well, the answer would be no, because it's not even defined at 3, game over. All right, now if something happens to be defined, then we check and see that the limit of f of x, as x approaches c, exists. So let's say the limit from the left equals the limit from the right. And that's a way to state that the limit exists. All right, so we're looking at, in fact, you could just say, you better check it, but you could actually say that the limit of f of x as x approaches c exists, and that means by default you checked it from the left and the right. And then number 3, all right, let's see how this could fall apart on us. Here's a picture. All right, say that I go out to 2 and I get 3, and I'm trying to see if it's continuous at x equals 2. All right, well, there is an f of 2. F of 2 is 3. So let's color that in a different color so you can see where I'm drawing. F of 2 is 3, so f of c is defined. But say the function looks like this, and that point just happened to kind of be an anomaly in the situation of everybody else is doing this except for right dead on that infinitely small point 2. So the limit does exist. There is a limit from the left and the right. But this fails to be continuous. How could I make it continuous? Is if I could move this, if I could move this down here, then it would be continuous, if only that was that, okay? So the way it would be continuous is if f of c is defined, there is a dot at f of c, okay? The limit of f of x as x approaches c exists, and those are one and the same. Then it's continuous. Okay, so then your f of c has to actually equal the limit of f of x as x approaches c. So let me do that on a clean slide. This is your definition of continuity at a point. And you would have to show these three things. If you have decided it's continuous, you could just launch in and say the limit of f of x as x approaches c equals f of c. That means that you've checked f of c is indeed defined, And if that's not true, then it's discontinuous at that point. But if it passes that inspection just because there's a point there, then we need to take the limit of f of x as x approaches c. It needs to exist. If that limit does not exist, then it's also game over. If your limit is you get close to a number, here's a great example. As you get close to a number, it's defined, but it does this. Okay, so here f of c is defined right here, right there, but the limit doesn't exist, and you can easily see that's not continuous. So what has to happen is f of c has to be defined. The limit of f of c as x approaches c, implied from the left and the right, does exist. And then number 3, that the y value at c and the limit of f of x as x approaches c are the same thing. By default, this says all 3 things, or you could just list them out, all 3. If you find out it's discontinuous, you state the reason why. You could get all the way down to this part. You could say f of 7 is defined. The limit of f of x as x approaches 7 exists, but maybe these 2 things aren't equal, so it's discontinuous for that reason. And so we'll be doing that. All right, discuss the continuity of each function. This one is discontinuous at x equals 1. That's kind of enough said right now. All right, on this one, I wonder if I know that it's discontinuous at x equals -2, but let's fill -2 in the top. This one right here is discontinuous at 1 because you have a vertical asymptote. It looks like this, and it's infinite discontinuity. All right, if I fill in -2 here, I get 4 minus 2 minus 6 over x plus 2, so -2 plus 2. Sorry, I didn't mean to do that. So anyway, if I fill in -2 right here, that's going to give me 8 minus 2 minus 6 over -2 plus 2, which gives me, if I did that right, 0 over 0. So this one probably has point discontinuity, and it has a hole in the graph, but either way it's discontinuous at -2 if they say to discuss the continuity of the function. All right, so this one, f of 1 is not defined. That's the word is not defined. All right, so the function is not even defined at f of 1. All right, this one is also true. F of 2 does not exist or is not defined. It'd be a little bit different situation because this would have a hole. And here, let's see if this is continuous or discontinuous. On a piecewise function, it's always good to start, even though this is less than. Less than doesn't mean less than 1 like 0. It means 0.999. So I do go in and fill in 1 right here and leave an open circle. If I fill in 1 right here, I get 1. And then I fill in 1 right here, and a lot of times it'll pick up and do something. In this case, when I fill in 1 right here, 1 squared is 1, and so this actually picks up where the other one left off. And so don't like do a little dot with an open circle, like that's really colored in. Of course, you don't need to make it that big of a blob, but in fact, let me draw this better now. -2x plus 3 looks like this. It's coming down, and you have an open circle, and then this one snapped onto it and picked up where it left off. So this one is continuous if I'm discussing the continuity of the function. All right, so let's check and see how we would verify on a test that something is continuous. First of all, I would check and see if f of 1 is defined. Okay, number 1. F of 1 is defined right here. I definitely have the 0.11. All right, number 2. Is there a limit of f of x as x approaches 1? Does it exist? Okay, let's see. If I come at 1 from the left, butting up right up next to 1, I'm headed toward 1, 1 as I come this way from the left, and from the right I'm on this part of the parabola, and as I come at it this way, and everybody's heading toward 1, 1, so the limit does exist. And number 3, f of 1 was defined. F of 1 was defined right here. the limit of f of x exists right here, like this, from the left and the right. And so then we find that we can make our final statement, f of 1 actually equals the limit of f of x as x approaches 1. And so this one is continuous. Even though it's piecewise, I can draw this line and it goes right into this curve. I want to make a point for something later though. It's still kind of like herky-jerky, kind of a corner there that's not important right now. It's continuous, but that'll come up later. All right, now what we're going to do is we're going to make it continuous. And so how do we make something continuous? First of all, let's find f of 1. Determine the value of k so that the function is continuous. You would expect to see this on a test. It really tests to see if you know continuity. They ask this often on the AP exam. All right, f of 1 is 8. Like actually where x is equal to 1, I filled that in and I got 8. Now I want them to meet each other. And so I want to fill 1 into here, and if they're actually going to connect, then the second part at 1 needs to be 8. So I'm going to say x plus k needs to equal 8 when x is 1 at that moment. 1 in here and 1 in here need to be the same thing. So k would have to be 7. Now let's look at that. That gives me g of x is equal to x squared plus 7 if x is greater than 1, and x plus k if x is less than 1. This was greater than or equal to. If I graph that and I fill in 1 and I go greater than, I start at 8 and it's a closed circle and it's kind of probably a little bit steeper parabola like that. This one, if I make this one x plus 7 and I fill in 1 right here, there's a hole at 8, but as I go to draw this hole on 8 right there, there's already a dot there, so like the hole picks up and my graph is coming toward it like this. You would need to mark off more units, but it comes from the line into the curve in one continuous fluid motion. Now if they ask me, you don't want to say the words like meet or connects on an AP exam or on one of my tests. So what you would say is you would say, now you know it's continuous because f of 1 equals the limit of f of x as x approaches 1. In other words, f of 1 is 8, and then you also made the limit of f of x as x approaches 1. You made it 8 because you checked it from the left and the right. All right, let's go down to this one and make the function continuous. All right, so I'm going to have this function, which is actually hard to see that number. Let me see, I have it on my computer. It's kind of fuzzy for me. I think it's x to the 4th, but I'm not sure. Yeah, x to the 4th. All right, so if f is not equal to 1, so they just left 1 point out of this, which is kind of good because you couldn't have filled 1 into this anyway. X to the 4th minus 1 is x squared plus 1, x squared minus 1 over x minus 1, which continues to be x squared plus 1 times x plus 1, x minus 1 over x minus 1, factoring the difference of squares. And so this function, for all practical purposes, will behave like this right here. And so I'm trying to think if I would know even what that looks like without my calculator. You can distribute and find values, but I'm going to, it's going to be a cubed function. I'm just going to put this leftover part, or you can put this part. Either way, it'll show you what it looks like. If you want to, you can just put the original into your calculator. And if you were stressed, if you were under the constraints of not having a calculator on this, you would find a lot of points and your model for an x cubed graph. So right now I'm putting in my calculator x to the 4th minus 1 over x minus 1. And because I factored and canceled, I'm going to get some sort of cubed looking graph on Zoom 6. All right, so I can go to table and find some points. I think 0 gives us 1, and I could do that in my head. And -1 is one of our zeros, and apparently it looks a lot like this, except for it has a hole in it at 1. If you verify in table, it never equals 1. So there's a hole in the graph at 1. Okay. And now what I want to do is now create a point 1 comma something. I want to fill in that hole. All right. So I know that this function, x to the 4th minus 1 over x minus 1, looks almost exactly like this function, x squared plus 1, x plus 1. Sorry, squeeze that in. Because all I did was throw out this 1 point. Now I want to reinstate 1 and give it the right value. I cannot fill 1 into this, but I can fill 1 into this. And to the naked eye on my calculator, these look exactly the same. So I factor and cancel and then see where the hole is. If I fill in 1 right here, I get 2. And if I fill in 1 right here, I get 2. And so the hole is at 1, 4. So I would want k to be 4. Now what happened is now I can say f of 1, which is defined right here with k is 4. F of 1 is defined, and it equals the limit of f of x as x approaches 1. Okay. All right, so properties of continuity. If b is a real number and f and g are continuous, then the following functions are also continuous. So you are able to say that if you take a continuous function and multiply it by like 4, it's still going to be continuous. The product of two continuous functions is also continuous, like sine x times cosine x. The sum and differences are also continuous. And the quotient is continuous, except for all the times that the bottom could be 0. You got to watch out for that, obviously, like the one we just did. This is continuous, and this is continuous. If you check those are defined everywhere. They're continuous everywhere. They're polynomials. Polynomials are continuous everywhere. But if I did the quotient to that, all of a sudden I have a discontinuity point where I could run into 0. Okay, so we're going to stop there for now, and then your next little video I'll pick up on showing you the intermediate value theorem. In fact, I think we'll just wait for intermediate value theorem until the next class. And so now your job is to work 1 through 11 on the worksheet that is attached to your homework assignment, and also do one of those problems on Flipgrid. On your assignment there'll also be a code, and hopefully you know how to go into Flipgrid and just show yourself working one of the problems. If you're working it with your camera pointed to a sheet of notebook paper, or you're talking us through it, or you know how to work it on your tablet or your phone, or if you don't know what to do, just reach out to me and I'll help you out. Hopefully we won't get 15 number 3s. So when you get onto Flipgrid, if you're one of the first ones, just grab whatever number you want. When you get onto Flipgrid, if somebody's already taken the numbers you feel good about, just go in and redo it. It might be good to see 2 people do number 5, for instance. But also some of you will be proud you got that whatever answer you got right, and you want to show us that. I will provide you the answers to the worksheet